Good morning. I'm Katie Cottingham, and welcome to this news briefing from the 251st National Meeting and Exposition of the American Chemical Society in San Diego. We're joined today by Dr. Vijaya Rangari and Boniface Tiimob from Tuskegee University. They will be talking to us about using eggshell nanoparticles in biodegradable packaging. Dr. Rangari?
Good morning, and also I would like to thank ACS for giving this opportunity to share our interesting results on the eggshell nanoparticles. And also the National Science Foundation is the one actually supported our work from last several years, and they are continuing our support. So I would like to thank them for their financial support. So actually this is all started when we are looking for these sustainable waste materials where we can use it as a nanoparticles. So that's where we look into the literature, and we easily, quickly realize that there is a lot of waste eggshell is available, and this can be used for the value-added products or useful products. So that's where we started our looking into eggshell nanoparticles, and we come to know that we're next to Atlanta, where in Georgia there is American Dehydrated Food. They produce a lot of eggshells, like tons of eggshells in the waste, and also most of them they use it as a landfill. So that's a financial burden for the industry. So that's where we get our eggshells, and we process them and get into the nano size. So once you get into the nano size of these nanoparticles, that's where start all the activity. Basically the usefulness of this material compared to the rock or other calcium carbonate nanoparticles. So the several applications, including from the polymer nanocomposites as a filler, and also biomedical engineering applications or biomedical sciences, were used for the tissue engineering or antimicrobial activity and those kind of things. And so that's where we started in this presentation. What we had this ACS meeting, we are working on this biodegradable polymer composite, where we use this very unique eggshell nanoparticles. Like they are very highly porous and also platelet-like structures. These we infuse them in the biodegradable polymer blend, PBAT and PLA blend. So in that we use only just 0.5% of nanoparticles, and they increase the strength and flexibility. Basically, the flexibility increases around 700 times. So that's what makes this material will be very useful for the food packaging applications. And also we are working on this material with the antimicrobial food packaging or any other applications we can extend on that. And these calcium carbonate nanoparticles we are also using for the other nanoparticles, can make it like hydroxyapatite or calcium silicate, any other calcium-based material which are biocompatible and useful for medical applications.
Okay, thank you. Do we have questions? Please state your name and affiliation before you ask a question. Microphone's coming around. Kath.
So it's Kath O'Driscoll from Chemistry and Industry magazine. How expensive are the nanoparticles that you're producing?
Basically, the raw material is basically easy to is free to pick up. Raw material is not expensive. Only the processing goes around with this. The processing also not very tedious process. Only the one step where we have a ball milling process. So that is like a floor mill. People use it in a large tons of quantity. People make these kind of materials. And the one step is important is the sonochemical method. So that's where it takes a lot of some of this cost.
And what's the size range of the nanoparticles?
These nanoparticles are around 10 nanometer square, 10 nanometer size nanoparticles. So if you the EM image, it is a platelet structure.
To follow on to Pat's question about the biodegradability, under what conditions do they biodegrade? If this is for plastic wrap, for example, like you wouldn't want it to biodegrade in the store while it's sitting on a shelf?
They don't biodegrade in the store. They biodegrade unless until you put it in the soil, some acidic or basic conditions. So those kind of things only it will degrade. It doesn't degrade in the room temperature and outside temperatures.
Yeah, the PBAT polymer can degrade by hydrolysis in a moisture condition. Water is able to hydrolyze the bond between PBAT and then the aliphatic region of the inner polymer. Calcium carbonate dissolves, it dissociates immediately to calcium ion and then the carbonate ion, which, as he explained, the carbonate ion helps to step up the soil pH to create an enabling environment whereby the plant can uptake nutrients. The calcium serves as a plant supplement. And in most of the times, if you look, the crops that have lycopene in them, like tomato and the rest, those that have the red color, they have a condition called blossom end rot. And that is a calcium deficiency. So if we are able to avoid that deficiency by putting calcium carbonate or eggshell, for that matter, in this material, when it degrades, it will be most helpful to the plant, especially vegetables.
Okay, other questions in the back?
So how does your bioplastic compare to commercial plastics that are currently used in food wrapping or plastic bags? And have you optimized your plastic so it's ready to go to the market?
Yeah, most of the biocompatible or biodegradable polymers outside, they don't have, like we have this in the nanoparticles. Most of them are not. And also these polymers are very flexible, and also it's good for the soil. That's what it's not there in most of the other biodegradable polymers.
It compares really very well when you look at the applications like packaging, where we require flexible materials. Like in the glossaries, this material can stretch as much as 700 times without failing, which means that when you put a load that it can, and most of the glossary applications, the load is not much. We have the properties that can let this material play that role, and it's flexible enough to support that load. So it compares really well.
Actually, we are looking at more on this antimicrobial activity. So we are adding these calcium carbonate nanoparticles as a matrix, and adding other silver or other nanoparticles, antimicrobial activity. So we can make a film out of antimicrobial film that can be used for the food packaging, for the E. coli or salmonella, something can avoid it, the contamination in the future.
Okay, over here.
Good morning, Sam Tracy, Chemistry World. Does the manufacturing technique make it expensive to produce, or does it limit the amount that you can produce each day?
No, not at all. See, the manufacturing process, we are using an extrusion process. So that's where the industry uses the same process now, the blow molding or a thin film manufacturing. So the one I showed in the image, that's it is smaller version of this extrusion in the lab scale, but that's where the industry uses. So it is the same conditions we can apply to the large scale production. There is no difference in that. That's the reason we stick it to the polymer and the process, and everything is what industry is using. There is nothing to change there. Only thing is our new idea is making into the nanoparticles unique.
And the nanoparticles too, the amount that we use in this material is very insignificant.
Yeah, it's a
and
0.5%.
that is the good thing about nanoparticles. You don't really need to add so much to get desired what you see in this
just for the boiling water. And you take it out most of the organic contents and whatever they from the where come from the industries sometimes. So once you get that, and the next step is you make into a simple flour mill, like where you use the wheat and all those things, flour mills. You can use it to get into the micron size. So you crush them into powder like a flour, like wheat flour or something. So that is much easier process. The industry uses tons of quantity. So until that, there is nothing much involved in that. But the second step, where we're using the ultrasound to make into the nano size, so that's where it takes some of the effort to get into the nano size. So that's the only size. But the way you were looking at, we're adding a 0.5% of the whole system. So it's a very small quantity of the nanoparticle we're adding it. So cost effective, we've not done the cost analysis, but in my opinion, it may not cost whatever we have in the market.
Now, how about the transparency of the film?
It is pretty transparent because we're adding a small percentage, and that too, little bit of a whitish color it comes, but it's not at all. 0.5% is very small.
So it's basically a nice material to
yes.
Wrap chickens in or something.
Oh yes, the more interesting is polymer. This is one of them, flexibility. But our more motivation is more come from the biomedical applications. Think about this can use for the dental applications like a calcium silicate, dental filling applications, or like a tissue engineering like a hydroxyapatite. We make these calcium carbonate nanoparticles using as a main ingredient and make hydroxyapatite, and that can be biocompatible and can use for the bone regeneration applications. And also we worked extensively on the drug delivery application. So where calcium carbonate is highly porous, we fill it in the toxic drug like a cancer drugs or those colon cancer, those kind of drugs, and fill it in, and when you go into the pill, or if you take it as a pill, you go into the stomach and it will dissolve because if the pH hits it higher, calcium carbonate dissociates. When dissociate, drug releases from there, and that we can be used for the application where you need most of the drug, like a colon area, those kind of things.
Well, I presume the nanoparticles are primarily calcium carbonate and
yes,
calcium
everything
phosphate.
is calcium carbonate. Only thing is biocompatibility comes from some of the protein which is where eggshell build up. So that we cannot take it out. We want it to be there inside because that's where it makes it more biocompatible, better than the rock calcium carbonate.
Okay, we have an online question in the back.
Yeah, thank you.
So this question is from KM Kowalski for Science News for Students. And she's asking for a clarification. She says, on the increase in flexibility, is it 700 times more flexible or 700%?
700%.
Okay.
Yes.
Thank you.
Okay, and what will you do next?
Oh no, we are working on this extensively on the biomedical application side. So this is polymer fillers is a very small work, what we do it regular routinely in the lab. But our more interest is getting into now we are working on this antimicrobial water filtration application. So this, we take the calcium carbonate, large quantity, and we add a small quantity of the silver nanoparticles, and it will fill into the porosity of the calcium carbonate, and we can use it as a blend, and you can use it as just a filter material, like a water filter where we can drink it at home. So you put the material and pass through the water, so you can kill most of the bacteria like E. coli and staph and those kind of bacteria we can clean up. Even the main idea is because of this porosity of the calcium carbonate helps to trap all other elements which are there. And we can tune up this calcium carbonate with any other specific targets to absorb it. And this is a very cheap material, so we can use large quantities.
Okay. Okay, so if there aren't any other questions, thank you very much for joining us at this press conference. The archived version of the session will soon be posted at bit.ly/ACS Live San Diego. Please join us for our next press conference today at 9:30 on bug-inspired antibacterial surfaces. Thank you.